So we will be also I will be showing it all these things today, but I will not do the mathematics here today. I just try to show that we were calculating, say suppose this is a site, this is a site, and this site, and this is your fault, and this fault has a length of L, and we have a, say suppose at any time this length, some part of the fault get ruptured, and that is equals to your Lm, and that is located at a distance of Re from here, and we can calculate what is the probability of this fault to be get ruptured out of this entire fault, and that will be created a magnitude of m, which is greater than the magnitude of some numbers, right? So that is what we were trying to establish or trying to calculate, and so this, there is any part of the fault can rupture, and that is what we have to compute the probability. So that probability we will be calculating tomorrow, whenever we are doing all the area sources and the line sources, then we will be taking care of this part. Okay, so basically we have a various magnitude, and there are various distances from the site, and we need to compute the probability of mass distributions, and then we need to calculate that what will be the, at what point the maximum possibility of earthquake occurrence will take place. So this is your joint magnitude and distance distribution. So that is what we were interested to calculate, so that we know that this is your, say suppose this is your 5.0 to 8.0, this magnitude range, and for this magnitude range at a distance of from 0 to 60, when there is all possibility that there are various probability may occur, and it is a possibility that we have a at some distance for some magnitude there is a highest probability of occurrence, right? So that we need to calculate based on the data. So that is your probability things. Now, what are the main things I need to do is the this magnitude is one part. Magnitude is we can calculate on the magnitude, but there are a lot of other ground motion parameters that we are interested in. So this interested is the peak ground acceleration, PGD value, peak ground velocity values, spectral acceleration values, and or the duration values. So instead of calculating the probability of exceedance of the magnitude, we can also calculate the probability of exceedance of peak ground acceleration. We can also calculate the probability of exceedance of the spectral acceleration or the spectral velocity. So these are the things also we need to calculate. These are called intensity measures. Okay, so these are called intensity measure. So this is called IM. We always put the IM. Now this IM can be, depending upon your choice, you can put it IM as a peak ground acceleration, or IM as a spectral acceleration, whatever you like to do. Okay. Now I have already told you how to compute the spectral acceleration of the data, and that is that spectral acceleration with a 5% of critical damping. So this SAT equals to omega n square into this much. So that is what we have already calculated the response spectra. So you can compute the response spectra of the data and the spectral data. So so for a ground, if it is a oscillate, then it will be creating a displacement of the structure or this one. So that displacement is these displacement values, and that maximum value of this displacement multiplied by the omega n square will be the spectral acceleration, and that spectral acceleration you can also use as an intensity measure. Okay, right. So this is rupture and sites are given. So that means one fault is there. That fault rupture history is known to you, and the site is known to you. So for a given rupture and given site, we try to calculate what is the probability of any intensity measure, either it is a peak ground acceleration, peak ground velocity, or anything spectral acceleration, to exceed a certain value, right? So it should exceed a particular certain value. That is what we need to first calculate, right? So this will be equals to the this is basically based on the normal distribution data. So the normal distribution with a greater than x means it's a 1 minus. So 1 minus, this part is called the cumulative normal distribution, or the normal CDF, normal cumulative distribution. In MATLAB, these things you can calculate with the word norm CDF. So this P is equals to norm CDF, and give this number whatever you calculate here, and then it will be 1 minus of this one. That will be your probability, right? So the probability of exceedance, this one. So so this P part is equals to we call it as a standard. This is called standard normal distribution, or the cumulative values of standard normal distributions. So it's a cumulative values of the standard normal distribution. Okay, so this will be equals to phi. So what we do, we take the logarithmic of that exceedance, how much exceedance you are talking about, so ln x, minus this is your average mean value. So that means from the average value, how much is the exceedance that you calculate, and divided by the standard things. Okay, so basically we will assume that this will follow a normal distribution with your mean equals to mu this much, okay, mu of ln im. So this is your normal distribution. So this is your, this part is actually I am taking it back, it is a log normal distributions, right? So this is your log normal part, that's okay. And so it is a log cumulative, I think it is called the cumulative log normal distribution. So this is your log normal distribution, because this is in a log. So this is your mu value, and this is your standard deviations, right? So that is your standard deviation of sigma. So you can calculate this one. Now these things we can compute based on some of the ground motion model relation, right? So for every Jones, we have a ground motion model, GMM, we call it as a GMM, ground motion model relation. So based on that relation, we will calculate these numbers, and this is your observations, or you should expect this much of things to be excited so that you can calculate. Okay. Now let us see one example.
The images, as you say, in the relationship is to the effect comments. I mean, so in the previous slide for brother in estimated river of X. So what does it mean in this meter? Basically, when anything is possible.
So let's see your. This is one model. This is one ground motion model relation. This is called BFJ model. BFJ is a Bohr, the stochastic inversion you read with the Bohr, and then this is a Fumal and the joiner. So these are they have a model for the ground motion model. Now this ground motion model is given by this relation. So that model they had established by studying lot of earthquake and its attenuations. That means how the, say suppose some parameters, let's see, SA, okay, the spectral acceleration. This spectral acceleration with distance, they had calculated lot of actual values from the different earthquakes, right? And based on this earthquake relation, they had performed a regression analysis and got a relation, right? And these are based on, okay, whenever the first ground motion prediction equation or the ground motion model equation was been given, the very first one, the Allen Cornell of the Stanford University, they provide it only with the magnitude and distance, right? So only magnitude and distance. With a, say suppose the PGA value with the magnitude and distance, they had established a relation. But as the more data comes in, we had seen that the magnitude and distance, although it is a very important parameters, but it is not all. We have a lot of other parameters are involved. Say suppose what is the type of the soil, that will influence the spectral values or the PGA values, okay? Then what type of faulting it is, that is also gives the value from the different spectral values, right? So all other factors are also involved there. So as the time goes, there might be a 8 to 10 parameters with lot of other influencing parameters are all present. So now the ground motion prediction equation or ground motion model equation is really a complicated one. Okay, but that's okay. We are getting much more control data, and that is good for our realistic estimations. So this is what we were trying to calculate. So this regression analysis will give you this type of A1, A2, A3, A4, A5, this type of relation. There is a table, big table, and so this regression values for different spectral frequency, we all have these numbers, right? So for a strike slip fault, and for a S equals to 1 second, let's see, at 1 second spectral acceleration, this relation by substituting this A1, A2, and A3 from the table, we can get that mu, that means the mean value of the ln SA at 1 second equals to minus 3.14. So that is equals to your A0. This is your A1. This is your A2. Okay, so this is your A0. This is your A1. This is your A2. This is your A3. And this is your A4. And this is your A5. Right. So this you can read from the table. So that if you know that, then you can calculate this one, and sigma ln SA, so this is your log normal, the spectral acceleration, so that is equals to A6, so that will be equals to 0.52, right? So that A6 is 0.52 for 1 second. So that model will give you these numbers, and you can calculate for 1 second if you try to exceed or try to compute what will be the spectral acceleration at 1 second to exceed some value, say 2.5 centimeter per second for a given rupture and given site, so that this 2.5 will be coming here, and we calculate mu ln m from this relation, because that value you can now calculate with your distance r if it is a given the site, and the magnitude values if you can provide, then you can calculate the mu ln SA. And similarly, there was another model. It is called Chiu and Young model of CY14. This is for the these are some of the models we are using for the NGA OS2 empirical database. This is a big database for this type of model, has been given in the NGA OS2 model, and there are 11 predictor variables. The predictor variables are basically what is called the mass, the magnitude, distance, and the VS30. These are the only things we are using it. So these are the 3 predictor variables. So, but there are the Chiu and Yang, they have 11 this type of predictor variables. So that means strike fault normal, strike fault fault normal, this one. So they have a lot of variable, and based on that we can compute these numbers. Okay, so this is the NGA OS2 model. I do not know how up to which year it has been plotted. I forget about that, but this is your spectral acceleration of all the recorded earthquake, whatever it is available in the world. So they had plot for the different magnitude of the earthquake, right? So 8 magnitude earthquake up to because 8 magnitude is very few. So but we have all the spectral acceleration values. This is modeled by the CY14. I think this is the CY14. Yes. So this is the CY14, and this is the data for the BFJ, this model and the CY14 model. So they had tried to calculate this regression analysis, and these are only for 10 to 20 kilometer distance, right? So blue, and the blue is the lower distance, and the orange are for the large distance, so 80 to 100 kilometer distance. So they had taken that data and tried to model this one. Okay, so similarly, that spectral acceleration at 1 second for the at the very close distance for the magnitude 5.3 to 5.7. For the magnitude 5.3 to 5.7 is basically the blue line, and the magnitude of 7.3 to 7.7 is for this orange line. So that is also, we can see that's the one is the this is for the BJF model, BFJ model, and this is for the CY14 model, and this is also the BFJ model for the big one, and this is the CY model for the small magnitude. Okay, so So we are saying that the intensity measure depends on the hanging wall effect. The intensity measure depends on the depth of the occurrence of the earthquake. Intensity measure also depends on the rupture directivity. So yesterday I have told you that how the rupture directivity changes the amount of the peak values and hence the spectral acceleration, spectral velocity, and all these numbers. So this is your rupture directivity, and then the style of faulting, if it is a strike slip fault, if it is a reverse fault, or what type of fault it is there. So that also depends, and the long period site response effect we have to also calculate, right? Now, what I need to do is this, that we need to calculate the rate of certain intensity measure, right? So let's see, the intensity measure is the spectral acceleration. So this is your lambda Im to be exceed a particular values, right? So that means spectral acceleration to exceed a particular value that we need to calculate. So that means this is the probability of this one. So this is your rate. So that is your probability multiplied by the rate of rupture that we need to calculate. So this is lambda is the rate associated with it. Okay, and then this is the ground motion model provide the probability of intensity measure exceeding a certain value. So this is the probability measure to exceed a certain value multiplied by the rate associated with the rupture will be the rate of certain intensity measure to exceed certain values, right? So let's see as a one rupture model, right? So just a single one source and one site, right? So let's see the predicted, the median from the Bood-FJ relation or any other relation, we get the mu value equals to 0.170 g, right? So that's your mean value we got, and the standard deviation also we got from the 0.5 this part, right? So that is your two number. You can get it from, for this relation we had found it out, right? So this number and this number we got it from the ground motion model, right? So this is the ground motion model, one model, BFJ or CY14, whatever it might be. But there are a lot of ground motion model available. So that we have given here, right? So these are, we have read from this and we know this number. And let's see the lambda rupture. I have given you this value. This is equals to 0.01, right? So this value is 0.01. So what I need to calculate, we want to find the probability that a rupture 1 earthquake will cause a spectral acceleration greater than 0.2 g. So we need to calculate what is the probability that with this given fault at this site, the spectral acceleration will becomes a 0.2 g. If it is possible, we have this data available to us, right? So that is what we have to calculate. So PSA 1 second to exceed for a 0.2 g, provided the first fault get rupture. So this is a rupture 1, right? So that is what we have to calculate. So that will be equals to 1 minus phi into ln x minus ln mu divided by sigma. So ln x equals to 0.2. So put this ln into 0.2 minus ln, this will be the mu. So ln mu equals to 0.170 and divided by ln SA. So this will be 0.520. Calculate this one will be equals to, if you do these things, this will be equals to 0.378. So this is your norm CDF, if you can calculate, then that will be equals to 0.378, right? So, but we have to calculate what is your annual rate of exceedance to be 0.2 g, right? So first I calculate the 0.2 g is how much. Then we have to calculate annual rate of exceedance to be 0.2 g. So that means I have to calculate lambda. So lambda equals to, therefore the probability, this part I have to use. So this is the probability part, we have used that, multiplied by the lambda rupture, and lambda rupture is equals to 0.001. So 0.378 into 0.01 equals to 0.00378, right? So that's your probability of exceedance of your one numbers. So that is one fault at that site. This site is a 10 kilometer that we used in our PFJ model, and then that we can directly calculate that. Okay, so so let's see that. Let's see if we can calculate for the 0.5 g. So earlier we have calculated for the 0.2 g. So let's see, calculate with the 0.5 g for the same thing, right? So there is nothing. Let's see, the magnitude is 6.5, the strike slip, I give you now the distance. So let's see, this distance is 10 kilometer. Let's see, Vs 30 equals to, so this is also true, true for this one too. This is the same thing. I have not changed this, anything, just only I said that this site will register 0.5 g. So what is that probability that this site can have 0.5 g with these ruptures, right? So that is what we need to calculate. Say at 1 second to be exceed a 0.5 g with a rupture 1, right? So that means 1 into ln 0.5 minus the same value 0.170 sigma ln equals to 0.520 divided this one 0.0191, right? So 0.0191, if you multiplied with your lambda rupture, here it is a 0.01, so that you can multiply it. So then this will be equals to 0.00191, right? So that is equals to what is the probability of 0.5 g. Make sense? So these things you can calculate directly with this, and then we can compute a curve. Okay, now for this is your annual exceedance, so that means this is your lambda values. Okay, annual exceedance, this is your lambda values, and this is your spectral acceleration. So spectral acceleration will be equals to, so 0.2 g. So 0.2 is here. So we can go up to the 0.2 here for the spectral acceleration is a 0.2 g. 1 second acceleration to get a 0.2 g is equals to 0.00379. So that will be equals to this value, right? That will be this value 0.00379. So that point we can calculate. So this will be equals to this value will be equals to 0.00378 values, right? And similarly at 0.5 hertz, 0.5 g spectral acceleration. So this is 2, 3, 4, and 5. So this 5 value 0.23 g. So that will be equals to here, and that value will be equals to 0.00191. So 0.000191. This is your 30191. So that is equals to here. So these 2 points you can plot, and then the join it with your line. So then that is your this is your ground motion hazard curve for your spectral acceleration, right? So that is your ground motion hazard curve for the spectral acceleration of 1 hertz. So that is what 1 second that you can calculate. So you need therefore 2 things. One is the a possible ground motion prediction model that you first need, from where you can calculate this mu value and also the sigma value, so that you can calculate that. And then you also need basically the lambda. So that means what is the rate of exceedance of that fault to have a magnitude of earthquake. So that you have to find it out. So these two parameters, if you need or if you have, you can calculate the ground motion hazard curve. Now what we do, or what we actually do the things, we have a in our calculation, whenever the ground motion hazard maps are prepared, we use the 5% exceedance or the 10% exceedance in basically 50 years, or 2% exceedance in 50 years. So that we all calculate this one. Okay. So that means we are trying to give a spectral exceedance of some particular numbers, and then we see that at that particular site, how much, what will be the spectral acceleration will be exceeded, right? So we do basically a reverse thing. We fix these numbers by anyone, and then draw this curve and get what will be the spectral acceleration of that particular area will be, and based on that we calculate this. Now if you have the two ruptures, so that means the fault is being bounded. Let me see if I have two ruptures. No. So that means there are two faults are here, and this is the site, right? So they have a rupture 1, and then this is a rupture 2, right? So this is your one is this one, which one is your previous one, and the rupture 2 might be the 7.5 magnitude earthquake. Let's see, R is 10, and lambda rupture equals to 0.002 times per year. So that means it will be ruptured with a 0.002 times per year. Okay, so these are the ruptures. Because it's a high magnitude, so if it is a large magnitude, then its per year occurrence will be much smaller than the small magnitude, relatively small magnitude earthquake. So that will be equals to lambda value will be much less, right? So let's see, our intensity measured is 1 second, so that will be fine. And so for the first one, we all know what is your mu ln SA and the mu sigma ln SA. But for the rupture 2, if we can calculate, this will be equals to 0.450 and 0.520, right? So this is the two values which we can use for the rupture 2. So if it is a two ruptured model, so let's do the rupture 2 part, because the rupture 1 we have already calculated. So for the rupture 2, so the spectral acceleration will be exceeded 0.5 g. Okay, so for the rupture 2, so this will be equals to this is 0.2 g, 0.2 g. Okay, first one is 0.2 g. So for the S equals to 0.2 g for the rupture 2, you just put this number, ln equals to 0.2, mu equals to 0.450, and this will be 0.520. So this is 9401, and then this has a the sigma value equals to the lambda value equals to 0.002, so multiplied it with a 0.002, so that's your 0.940.002, and the earlier the rupture one, it was 0.378. Let me see, this will be equals to 0.10 will be equals to 0.378 into 0.01, so 0.00378. So this is equals to 0.378 into 0.001. So you can calculate this is equals to this much, right? So similarly, the probability of 0.5g is the 0.5g value is here for the rupture 2 will be equals to ln 0.5 minus this value is already calculated 0.450, and then calculate this number equals to 0.419, right? And then 0.419, if you can put that, so then the rupture 1 and rupture 2, if you can combine, so this is 0.19 for the rupture 1, 0.01, and then this is 0.419.002. If you can calculate, this will be equals to 0.00103, right? So that's your lambda of this one. So if you can see this two curve, so this is for the rupture 1, this is your rupture 2, this is your rupture 2, and then this is your rupture 1, right? This part is equals to your rupture 1. Yeah, so this is your rupture 1. So then you can calculate these two fault, rupture 1 and rupture 2, and then add these two values to calculate the total things, right? So the total things, you can see it here, and that is your big one is the total, right? So this plus this is equals to this one, so that will be equals to the total. So this total ruptures, you can find it out, and from that, from the two sides, you can compute the. So that means you can see the at the lower value at the S1 1 second, the rupture 1 contributes much more. So because this is much more contribution by the rupture 1 than the rupture 2, right? At the lower stage, and at the rupture 2 scenario contribute more to the exceedance at the higher values, right? So okay, so this is what you have to compute for your.
So sorry, I just kind of probably missed the previous one. Like the rupture 2 scenario is under what sort of it was an environment? Certain like counts.
The total is the biggest black line or the thickest black line. So that is your
total hazard, okay? And then there are two, this is one here and other here. So this is the 1 and 2.
Does it make sense?
Yeah, so like rupture 2 is contributing both.
The rupture 1 is contributing what? Because this value is here, right? So at the low frequency, at the low
in this zone, at the spectral acceleration, it is equals to at 1 second, at the lower SA values, rupture 1 contributes more, okay? And the larger SA1, the rupture 2 contribute more, okay? So basically what I am trying to say is this, that my point is here that if I know the annual rate of exceedance and from a fault, what is the possibility of a magnitude earthquake to release, so that if I know this lambda value, and if I know the ground motion attenuation relation, what you are using it, so then it will be very easy to calculate any intensity measure, but you have to use the corresponding intensity measure attenuation relation. So usually the peak ground acceleration, SA at 1 second and SA at 0.2 second, these are usually been provided, right? So because of our the engineering design, usually 0.2 second, 1 second, and the 3 second, these are the values when any earthquake hazard part they will provide, and based on that value we can calculate the any fault, what will be the annual rate of exceedance of any intensity measures, right? So this is the case now. So if you see we can create a, say suppose if we know that one rupture value from this one, you can go on calculating the 0.2 G at a different magnitude, what it will be, we can also calculate, and for the different magnitude how it is becoming, and then probability of exceedance of 1 second to be greater than 0.2 G, that is also we can find it out after multiplying with your lambda rupture one. So this is your probability, and this is your probability multiplied by the rupture one, right? So then that you have to, you can calculate, and this is your lambda rupture one, so that you can also find it out from this relation. If you know, if you know the, say suppose 5.0, the rupture is this much, then for each one, how much will be the rupture value, you can calculate. So this table, if you can prepare, then any magnitude you can give, I can tell you that, okay, this will be the values, right? So, those similarly 0.5 G, you can calculate if this is your rupture value at 5.0 magnitude. 5.0 magnitude, what will be the rupture value? If I know that, I can calculate all this number, all the table very easily. Okay, and I will show you in one of the tutorial how to get these numbers, and then we can calculate by any prediction equation, any ground motion prediction equation with your magnitude and the distance and the type of the fault. You can create your all the intensity measures values, right? So that is the task today, and we will be learn a little bit more on the next day about how to calculate this one, and also the different type of source zone, what are the probability values, and all the little bit more details about the calculations. Okay, so